In class, we've been looking at the relationships between force and mass and acceleration. And we've seen some graphs that show us how force and acceleration show a direct relationship and how acceleration and mass show an inverse relationship. Let's use this to create a formula between F, M, and A that will allow us to predict things in the future. So first of all, if you have a direct relationship, it means that those two quantities can be shown on opposite sides of an equal sign. It's kind of like a teeter-totter or a balance, where the two sides have to sort of match. If one goes up, the other one has to also go up to maintain the equality. If you have an inverse relationship, those two quantities would show up on the same side of an equation. Because if one increases, the other one needs to decrease in the same way so that overall the amount does not change. And so this actually gives us our formula for what's called Newton's second law, that force is equal to mass times acceleration. We can use this to find force if we know mass and acceleration, to find acceleration if we know mass and force, or to find mass if we know force and acceleration. Key thing, like with all of our formulas, is if there are three variables, we need two of them, and then we should be able to predict or determine the third. Sometimes we have more than one force. We'll see an example of that in just a few minutes. And in that case, we would need to think about a net force instead, where we might add or subtract force vectors or force arrows in order to determine what the net force is. And then keep in mind that you could always bring in some old formulas in terms of motion and involve things like velocity and time with that acceleration from this sort of F equals ma formula. Let's take a look at a quick example that looks similar to something we saw in a lab in class. If we have 100 newtons acting on 50 kilograms, now that we've seen this formula, it should make sense as to why we saw an acceleration of 2 meters per second squared. Because that 100 newtons would have to equal 50 times 2. If instead we switch to 100 kilograms, we would expect that the acceleration would change. That force is now being asked to push a larger, more massive object that has more inertia, harder to move. And so we saw our acceleration go down. But it didn't just go down, a random amount. Specifically, it fits this formula, that if there's 100 newtons of force and 100 kilograms of mass, the acceleration would have to be 1 in order to maintain that relationship. We also looked at how changing the applied force can change the acceleration. So in the first case, again, it fits with what we see in this formula. We should have found that 2 meters per second squared would be the acceleration in this top case. In the bottom case, when we increase the force but keep the mass the same, it's going to be easier to move this object. It's going to move more quickly. It's going to accelerate at a greater rate. And so the block here accelerates at 4. We can see how that matches up with our formula here, that if 200 newtons is applied to 50 kilograms, 50 times 4 gives us that same 200. So it works out with things that we've seen. This example is the way problems are typically worded. We should be able to now use this formula to predict what something's acceleration would be. So let's look at the type of information that we're given so that we see how this formula F equals ma would help. From the information, and of course using units as sort of clues, our mass is 5 kilograms. The force that's given is 15 newtons, and we're asked to find the acceleration. So certainly our formula of F equals ma is going to be helpful. It involves everything that this problem deals with. But to find the acceleration, we would have to make a little bit of a change to that formula. We'd have to rearrange a bit, divide both sides by m, and see that division is the key math strategy here. So our acceleration would be the force divided by the mass, and we would get 3 meters per second squared. Now the units for this type of work are a little strange. It does turn out that a newton is sort of defined to be a kilogram times a meter per second squared. You don't necessarily have to remember that. The key thing is to notice that you're putting things into the formula in the right place, and that you understand what the standard units are for your result. So knowing that acceleration is measured in meters per second squared, that's how we determine how to label our answer in the end. In this example, we're asked instead to find a force, but we're given similar information that we've been talking about. Let's chart it out. Our mass is 2 kilograms. Again, use the units to help you see that that 2 is a mass value. Our acceleration is given to us as 8 meters per second squared. So to find the force, we can just use our F equals ma, and we can use it just as it is because it's already sort of set up to find force values. Plugging in our 2 kilograms and our 8 for the acceleration would give us 16. And again, the units are kind of odd, but knowing that all forces are measured in newtons when we use our standard units lets us know that the answer is 16 newtons. All right, this last question is a little bit more complex. Got a yellow star on there. Take a look at it. See how the information written in the problem does seem to be kind of simple. There doesn't seem to be a lot of information. But we're also given a diagram, type of force diagrams that we've seen before. So let's think about what we know and what we could find. We're given the acceleration. We're asked to find the mass. That's our question mark. And we would need to somehow involve the forces. Well, if you think back from this sort of diagram, we know how to find net force. And that's going to be kind of a little twist to these more challenging questions. It's not just 300 newtons or just 500 newtons that is pushing on this person. It's the combination of those two forces working against each other that would determine what her acceleration would be, and therefore what her mass we can determine. So let's figure out that net force first. Remember that if arrows are pointing in opposite directions, we would subtract the forces. So that would be 200 newtons from 500 minus 300. 200 newtons downward, that matches the direction of her acceleration as well. And then we'd be ready to use our F equals ma formula. I put in a little net there next to F net, next to the F. If you just call it F, that's fine, as long as you remember it needs to be the overall force, not just a single value of force. And again, we need to do a little rearranging because this problem is not asking us to calculate net force. It's asking us to use net force to find the mass. So we could divide both sides by A. Make sure we use the 200 newtons as our net force. Don't go back and use the diagram again. And we would get that her mass is 50 kilograms, which seems reasonable for a person.